Welcome, everyone. Today, we are taking a microscopic look at an absolute marvel of engineering design and cinematic presentation. We're going to break down a sequence that captures the transformation of a compact, unassuming gadget into a fully functional rescue drone. And the crazy part? It is all captured in a single, uninterrupted first-person take. No cuts, no slick editing transitions, just pure, unadulterated mechanical logic unfolding right in front of us. Okay, let's dive into this incredible explainer and see exactly how this clockwork ascent comes together.
Here is our roadmap for today. We'll follow this transformation in exact chronological order. We'll start with the setup and that initial click, then watch the chassis expand, the rotor arms deploy, and the sensors and landing gear lock into place. Finally, we'll unpack the underlying logic of the transformation and wrap up with a look at its cinematic realism.
Section 1. Setup and the initial click, the catalyst for transformation.
Every great mechanism needs a spark to set it in motion, right? Well, what makes this source material so compelling is that uninterrupted, single-take nature. Right at second 0, a right thumb pushes a highly visible orange safety switch located on top of this little rounded gadget. By second 1, that switch locks into place and you hear this deeply satisfying heavy mechanical click. The gadget is then gently placed onto a carbon fiber textured work table and the camera just holds perfectly steady. By second 3, the magic begins. You hear these crisp, metallic sounds as internal locking pins retract, signaling that deployment is officially underway.
Before we actually watch the chassis open up, we really need to understand the golden rule governing this entire sequence. It's called a physically believable transformation. Basically, this means the mechanical sequence relies entirely on the original volume of the gadget. Every single moving component you see comes from within. Think of it like the ultimate, high-tech Swiss Army knife. The whole shebang absolutely must fit inside that original casing. It utilizes actual physics. We're talking real hinges, sliding rails, and meshing gears, rather than relying on parts that just magically appear out of thin air. And honestly, this strict constraint is exactly what makes the engineering so deeply satisfying to watch.
Section 2. Expanding the core chassis, revealing the inner workings.
Okay, so the locking pins have retracted. Now visualize the gadget physically opening up. The deployment of the core chassis is incredibly sequential. Step 1. 4 symmetrical side panels cleanly separate along these pre-existing, clearly visible seams. Step 2. The panels rotate outward on precision hinges, and as they do, they expose this amazing array of compact gear trains, rotating shafts, and telescoping support rails inside. Then Step 3. The central body itself subtly widens. Actually, scratch that. It doesn't just widen, it physically pushes out using nested structural frames that slide smoothly to expand the footprint, all without ever violating the boundaries of that original compact volume.
Now, what's really interesting about this comparison is the stark contrast it draws to a lot of modern media. We so often see what you could call impossible expansion, where CGI shortcuts allow parts to just magically appear, and the volume changes arbitrarily without any physical logic. But what we're looking at here is strict mechanical logic. The volume remains totally consistent. That widening effect we just talked about is achieved purely because the engineers utilized nested frames and telescoping rails that were already cleverly packed inside. It is literally a masterclass in spatial efficiency.
Section 3. Deploying the rotor arms, taking shape.
With the chassis expanded, the drone now needs its primary mobility features. This arm deployment is a beautiful exercise in cause and effect engineering. First, 4 folded rotor arms extend one by one from their internal compartments. Next, they telescope smoothly outward to gain their necessary reach. Then, in just a brilliant mechanical maneuver, each arm rotates exactly 90 degrees to form a precise, perfectly balanced X-shaped configuration. Finally, they lock firmly into place. And just like that initial safety switch, this stage is confirmed with highly satisfying audible clicks. You can practically feel them lock.
But the arms themselves, they're really only half the story. At the end of each arm, we get this whole micro-narrative unfolding. Compact rotor hubs unpack themselves from layered circular components that were already cleverly contained within the body. From there, the actual rotor blades pivot outward from their tightly folded positions around each hub. They swing into place, snapping together to form complete, highly functional 4-blade propellers. It's totally ready for flight.
Section 4. Sensors and landing gear, preparing for operation. Let's move to and see how this builds our final functional form.
Because a rescue drone needs way more than just lift, right? It needs stability and it needs vision. That number 3 represents the 3 landing legs that emerge next. Deploying from these cleverly concealed lower panels,
These legs are absolutely crucial for establishing a perfectly stable tripod stance on our carbon fiber table.
We can actually systematically break down the mechanical logic used for each of these functional utilities. The landing legs, for instance, don't just awkwardly drop down. They gracefully unfold through multiple articulated joints and extend on telescoping sections to provide that rock-solid stability. Meanwhile, for vision, a compact forward-facing rescue camera slides cleanly out from the nose section on precision rails. And for scanning, a little sensor pod drops down and unfolds directly beneath the main body. Every single tool has its own bespoke, mechanically sound deployment method. And just before the physical transformation sequence officially completes, we get these final, fully automated micro-actions. Tiny navigation lights suddenly blink to life at the extreme ends of the newly deployed rotor arms. At the exact same time, cooling vents along the upper shell automatically snap open, preparing all those internal systems for the heat of operation.
Section 5. The Logic of Transformation, a masterclass in engineering.
Now that the drone is fully deployed, I want to take a step back and shift our focus to the underlying philosophy of what we just saw. I really want to highlight this specific quote from the source material. Throughout the transformation, every moving component originates from the original handheld gadget. I honestly cannot overstate how important this is. The designers committed completely to realism. Nothing was cheated. Nothing magically scaled up when you weren't looking. The entire, complex drone we see now was packed into that initial rounded shape. So the crucial point is that this sequence works so well because it intensely respects physical interactions. The precision gears mesh continuously without ever clipping through each other. Guide rails slide smoothly to extend reach. The hinges rotate, but they clearly do so with realistic resistance and weight. We can actually envision the miniature motors engaging to drive these complex systems, while heavy-duty locking mechanisms secure each stage safely so the drone doesn't just collapse back in on itself. This is premium industrial craftsmanship, simulated to absolute perfection.
Section 6. Cinematic Realism in Motion, the grand finale.
The transformation is complete. The drone rests naturally on its landing legs, and now it completely springs to life. The scene just comes alive with incredible macro detail. Those 4 newly formed propellers slowly begin spinning in perfect synchronization. And as they accelerate, they create this subtle airflow that actually stirs tiny particles of dust across the carbon fiber tabletop. It's wild. The camera gimbal wakes up, performing a smooth stabilization sweep. The sensor pod pivots, actively looking for survivors. The navigation lights pulse softly in a very specific rescue orange and white. And incredibly, right behind transparent inspection windows, you can see those exposed gears continuously turning. It is a photorealistic triumph.
And this brilliantly illustrates the sheer power of the camera work itself. Throughout all this chaotic, beautiful movement, all the sliding, the locking, the spinning, and scanning, the camera remains completely, unwaveringly steady. By keeping the shot uninterrupted and locked in place, it forces us to appreciate every single ounce of that satisfying mechanical engineering. There are zero fast cuts to hide imperfections here. The cinematic realism is laid entirely bare for us to scrutinize.
Which leaves us with this final, lingering thought. In an age of absolutely limitless CGI, where creators can make literally anything happen on screen with a few keystrokes, why do we still crave the deeply satisfying restrictions of realistic mechanical logic? Why is a gear turning and a telescoping arm locking into place so much more captivating to us than just pure magic? I think it's a profound testament to the beauty of physical engineering constraints. Thank you so much for diving into this fascinating explainer with me today. Keep asking questions, keep looking closely at how things are built, and I will catch you on the next one.